Good day, everybody. Welcome once again to Special Maths Academy. My name is Honor Pius, and in this video, we'll be looking at the final problem of the International Mathematics Olympiad 2022. So that's problem 6. Okay, so this is supposed to be the most difficult problem in this exam, and for a good reason, actually. So there are two main stumbling blocks, at least in my opinion, that makes this problem difficult. So the first is to understand the real essence of the problem, like what's it really all about, and then also to organize your thoughts so that the solution could flow in a nice way. Okay, so let's take a look at the problem. So we have positive integer n. So we say a square is a Nordic square. It is an n by n board containing odd integers from 1 to n squared, where each cell contains exactly one number. Okay, so two different cells are considered adjacent if they share a common side, and every cell that is adjacent only to cells containing larger numbers is called a valley. Okay, and then now we have an uphill path as a sequence of one or more cells. So it could be one, where the first cell has to be a valley. Okay, and then each subsequent cell in the sequence is adjacent to the previous cell, and the numbers written in the cells in the sequence are in increasing order. All right, so now the problem is to find, as a function of n, the smallest possible total number of uphill paths in a Nordic square. Okay, so there's nothing too special about a Nordic square, so just use an example, say n equal to 3. So this means we'll have a 3 by 3 board, so we'll have to deal with 9 numbers, so 1 up to 9. All right, so I'm just going to take a random arrangement of this. So saying it's Nordic just means there's nothing strange about it. So for example, no repetitions and things like that. But there's no hindrance in terms of the ordering. So you could just pick a random arrangement. So let's say 1, 2, 3, 4, 5, 6, let's say 7, maybe 8, 9. Okay, so this is already a Nordic square. All right, now for example, 5 will be adjacent to 7 because they share this side. All right, so that's just what it means to be adjacent. So now we can see that if we want to look at the number of parts, because we're interested in the this is what we want. So if we want to look at the parts, we have to first of all locate the valleys, because every part must start from a valley. So after inspection, we see that 1 and 3 are going to be valleys because all their neighbors are greater than itself. All right, contains number bigger than 8. All right, so we'll just list out this quickly. So we could have 1, 1, 2, 1 to 5. So we take in a very numeric order. So 1, 2, 5, 6, 1, 2, 5, 6, 1, 2, 5, 7, 1, 2, 5, 7, 9. Okay, we could have 1, 7, 1, 7, 9, or 1, 8, 1, 8, 9, or we could have 3, 3, 4, 3, 4, 9, 3, 6. Okay, that was the end for that. 3, 7, and 3, 7, 9. So all in all, we get 16 different parts that we could make. That is the uphill paths. So we just refer them to paths. By paths we mean uphill paths. Okay. So what we just got right now is the total number of uphill paths in this our specific Nordic square. So this is just a possible number for this particular n equal to 3. So there are other possible ones we could get, and then what we're interested in is the smallest of all those numbers. So 16 is just one of them. We have to check all of them to get the smallest. So now going about it this way is not actually a good way about solving this problem. That's because, for example, just n equal to 3. What does it take? We have to check every single permutation of numbers 1 to 9 in these squares, in these cells. And that's because once we swap any two, for instance, the set of neighborhoods or the set of adjacent cells will be different. So we expect a different list of numbers. The total value may not change, but definitely the sequences or the parts we are dealing with will change. So what does that mean? So we have to deal with 9 factorial different Nordic squares, or if we consider rotations and uh, reflections to be the same, then at most this is just going to reduce it a bit, but we still have a very large number of squares to deal with. And that's just for n equal to 3. If we take it just a step further to n equal to 4, you see that this is going to increase all the way to like 16 factorial or thereabout, and the complication of getting the paths is also a bit more. So, and this is just n3 n equal to 4, so it is not really a practical way to go about the problem, and we wouldn't even have enough examples to check for patterns. So we have to come up with a nicer way of going about this that captures the information we need without having to actually write out the sequence. Okay, so we're going to just show you what we could do. So we would use some sort of a graph to represent these numbers. So the arrows here are going to indicate the direction. That's an uphill direction. So to look like this. Okay. This comes down. So from this now, we see that we can trace the number of paths. First of all, we have the valleys, which one here, another one here, and we can see that they all have like outward arrows coming out from them. So ultimately, we have one path for each of them as valleys. Okay, then beyond that, we can get the others, the number of paths on each other that ends at each path. So we could have, for example, here we have only one path reaching up to 2, one path reaching up to 8. For 5, we have one path which has to pass through 2 to reach up to 5. Then for 4, one path as well. Now, if you look at 6, we see that we could have 2 ways of coming into 6, through 3 or through 5, and there is one way for each of them. So ultimately, we get a total of 2. The same is going to apply for 7. This time we get 3 paths in total. Then for 9, we see that we have one path coming through 4, 1 through 8, and we could have 3 coming through 9. So that gives a total of 5 paths. So with this, we could just collect the total without having to list this out. We have 4 here, 9, 3. So if you add this up, you get 7 and 9, that's 16, and we're done. Okay, so this means that we don't really need to know exactly what the numbers actually are. Once we've drawn this arrow, we can actually figure out the number of paths. So it's not really about the number, it's about this setup of arrows in this grid format. All right, so if you want to know how big or how small this could be, it means that we have to consider like how large these numbers we've written could be. So these numbers are the number of paths up to that point. So we're going to define, so let's k be one of these numbers of interest in the grid. Okay, so we'll say v of k is the number of paths that ends at k. Okay, so that's just what we have here. And of course, we know now that what we need is to just add all this from 1 up to n squared. So add all the k's, and that will give us a value that is the total number of paths, because every path must have a beginning, which is a valley, but it also must have an ending. And so we are just keeping track of based on the ending. So we have split them into different categories based on the ending. So for example, now if we look at those ending at 7, right, they will be this one, this, and this. So that's like one group. So we group them based on their endings, and then we have each of these v's. So if you add it up, we just get the entire collection of paths. So we get total number of paths for this specific Nordic square. All right, so meaning that we want to find the smallest this could be. We're assuming that n is fixed, right? So n is fixed. You're not changing this. So we want to see how small can this be, and maybe we could write that in terms of n, because it could be different for different values of n. Okay, so the first observation will make claim 1, or I should say claim, let's say claim 0. Okay, so there are no circles. Okay, so I'll refer to this as a flow, or kind of a network. Just refer to it as a flow. So by circles, we mean that whereby we can start from one of the vertices and follow the arrows and end up back at that same point. So that would be a circle. So we're saying there are no circles, so it's not possible to go around and get back to the same vertex. So why is that? And that's because of each of these arrow means we are going uphill, so we are going to a higher number. So if we start from A and we have an arrow going to B, going to C, and so on, this means that A will be less than B, be less than C, and so on. So suppose we get back to A at some point, then it just means that A will be less than A, and that will be a contradiction. So that's all we need here. So we'll be using this idea once in a while. Okay, then the main claim we need right now is that this will always be at least 1. So what does this mean? It means that for every k, there's always going to be at least one part that ends at k. So if k is a valley, we are done, because valleys on their own self are actually just a path. So if k is a valley, we are good to go. If k is not a valley, so what do we need? So if k is not a valley, what it means is that we could have, since it's not a valley, it means that there's going to be an adjacent cell, right, that is lower than, in terms of value, lower than k, that contains a number lower than k. So let's say that number is a. So it means that we have an a adjacent to k that's lower than it, so we must have an arrow like this. We'll repeat the same process. If a is not a valley, we continue like this. So we keep doing this, and we know that they have inequalities attached to them. So this is going to be a decreasing sequence, right? And we know that we only have a finite number of terms you could have in this sequence, and we keep going downwards. So since it's bounded below, we must have a point where this cannot happen anymore. So there's going to be some value that we cannot go down any further. So that would mean that we cannot find any other number beside adjacent to it that has a lesser number in it. Okay, so this would mean that this would be a valley. And once you have a valley, we could just trace back up here, and this is going to be an uphill path. Okay, so that's all for this. So based on this, we can now write so we can now define this, which I'll call accumulation. So this will be the main focus, which is going to be at least 0. So I'll call this the accumulation at k. So this means that at least all of them has at least one part, but some could have more. So this kind of measures the extra parts we get. Why we'll be interested in this is because this, for example, means at the minimum, for when n is 3, that will need at least 9 parts, because each of these will have a number that's at least 1. So how bigger can it get than that will depend on how much higher some of these numbers could grow. Okay, so let's take a look at the same example, but in terms of just accumulation, and see if we can get a good sense of what's going on. So this is a very crucial step. So I'm just going to redraw the flow for the same example. Okay, so we just subtract 1 from all the values we had up here. So we have 0 here, 0, 0, 0, 2, 4, 0, 0, 1. Okay, so let's see what happens. First of all, we have a valley. We had valleys here, so there's no accumulation here. And once they pass on to one order, we see that it carries on the same value. So up to this point, it's all 0. So the first value where we get something bigger than 0 happens where we have what I'll call a clash. So there's a clash here because there are now two uphill adjacent cells leading up to 1, and each of them will produce at least one part, right? So each of them will produce, in this sense, they'll carry over these accumulations. Together with the fact that we have a clash, we're going to get an extra 1. Okay, and then for this one, we could picture it as saying, okay, each of these carry over 0, and now we have a clash here, but of a higher degree. So this time there are 3 uphill adjacent parts clashing together. So we could see it as 1 appearing here and then an extra 1 coming in. So this kind of raises it up to 2. Now for 4, you can see it as, okay, we have this accumulation at 2, it's already here, plus the zeros, and then we have a similar scenario where we have 3 arrows coming together. So that would be a second order clash. So that will add 2 to it. So this is like a way of making sense out of these values. And so what we want to do now is basically reduce these values as much as possible. So the first phenomenon we'll keep note of is that when we had 2 here, it carried over to 4 here and even increased. So this means that if we want to reduce the total number as much as possible, we'll try to make sure that the larger numbers don't travel much longer than they should. The more they travel, the more that value is going to keep multiplying across the board. And also that once we have a clash, it's going to increase the number at that point. So meaning that in general, if we want to reduce this to a minimum, first of all, we want to reduce the number of clashes as much as possible. And then once we have clashes, we want to make sure they don't carry over as much as possible. So those would be like the 2 objectives. And this way we can actually use to measure how much things could grow, depending on the number of clashes in some sense, and how much they could potentially carry over. So now we'll look at the next claim. So claim 2. Okay, so this claim is about a square. So this will be a unit square. So what I mean by unit square in this sense is that once we have a flow, you could observe that we have like 4 squares here. Mind you, these squares are not cells. The cells are the vertices of this our flow. So they form this kind of square figures. So this is what I'm calling a unit square, or just a square. All right. So if you look at the square alone, we'll see that there are actually kind of 3 major patterns you could have. Because for a square, we must have 4 vertices, and they are all adjacent in this sense as a square. We have arrows pointing in different directions. So we're going to take the scenarios based on how numbers are arranged. So let's say we had the number A here as the smallest among the 4 numbers. Then the greatest number among them could be up here, or it could be adjacent to A. So let's say up here. Now, if the greatest number is D, then there's only one way we can go uphill along this square. So to have to go like this, and we have another way this way. So this is the only flow we could get from this. We don't have much of a choice here. Meanwhile, if we have adjacent, definitely we go uphill here, and we go uphill from A as is the smallest, and we go uphill up to D as D is the greatest. But the last part, we could have 2 options. So that's what makes them 3 in total. So still have the same setup. Okay, excuse me. So we have, it could go down or it could go up. So if it goes down, it means that we have something smaller here. So maybe B and C, and in this case, maybe B, and then C. All right. So these are the three major setups you could have. So what I'm going to do is for each square, we're going to have where we have a clash. So that will be a peak. I'll call it a peak of the square. So this will be a peak, and it will be of major interest to us. Here we'll have two peaks because we have one at D, but actually we have another one at C, and then finally we have one at D here. Okay, so what can we observe? So based on the accumulations, we see that for this first scenario, I'm going to draw this now based on accumulations. Okay, so we have something like this, peak. So I'm doing all this because it gives us a good intuition about how we might want to solve this problem and what the answers could actually look like as well. So we have another peak here. All right, so we already know the values, so I'm just gonna, here we have two values actually. So for the values, the accumulations were originally 0. Sorry. So we have 0 here. All right, and then they're going to carry over. We have 0 here. This carries over 0. Now once we have a clash plus the sum of those zeros, you just get 1 here. And here we get a clash, so we get 1 here, we get 1 here. Carries over 0, carries over 0, we get 1 here. Okay, so for every extra arrow that forms a clash, we get an extra value added to the sum. Okay, so if you look at it this way, we see that it means that in this square, that the accumulation at the peak has to be at least 1. Where K is a peak of T. So why is that? Now in this figure, clearly we have 1, but then it's possible that it's not isolated in the sense that there's a bigger picture. Let's take a look at the first one, for example. You could have this as a square, but it could just be a small part of a bigger picture where we have other things going on, right? So it's not isolated. So we see that if we had like a clash before we had that valley, meaning it's not actually a true valley, we see that clash would mean that there will be at least some accumulation carried over. It could still be 0, but it could be higher. And if it's higher, it's also going to carry over. And if there are extra clashes, it could still increase. So it can only get higher, right? Or it will remain the same. And to do that until we get back here, which will definitely still increase because we already have this clash. So because of the clash alone, it means we have at least 1. And if we have clashes before then, it's only going to increase much more. So this means, and once it's increased once, for example, at the valley, you see that it's going to, let's say we have accumulation now 1 here. This will become 1, this will be 1, and this will become 1 plus 1 plus the clash, which is going to be 4. So see that if we take the total now, it's going to be much different than the value of 1 we would have had here. So here we now get total of 7 instead of 1, just because of a single accumulation that was carried over here. So this means that we want to definitely make sure that accumulations are not carried over as much as possible. Okay, so this is going to be the basis of what we're going to do next. So now we're going to create a partitioning. We're going to create a partitioning of squares. So we're going to create 2 sets. So let S be the set of squares or unit squares. T. Okay, and then let U be the set K such that K is a peak of some square. Let's say T. Okay, so this will be the basis of what we'll be working on. So now we're going to use an algorithm to create something that will be quite useful in terms of estimating the bound. So what we're going to do is we're going to associate with every square a peak of it. So every square will have at least one peak. We'll associate it with a particular peak in a way that we can estimate the overall accumulations based on each square. Okay, so here's the algorithm. So initially, we'll assume that we've not assigned any values. We have not assigned any k and t. So we pick a k. So if k is in U, that's a peak of some t that is not yet assigned. So we are trying to partition it. So for each k, we use that to partition the squares that is not yet assigned. And we have that k is let's say peak of let's say this squares t1, t2 up to tm. If you look at t1, k is a peak of t1. If you look at t2, k is a peak of t2. So we list out all of them that are not yet assigned. So okay, and then simply we just assign, then we set. Okay, and sorry, one more condition, and the accumulation at k is actually more than the number of these squares. Then we assign this to one partition, which will denote as sk, to be t1, t2 up to tm. So let me explain what this means. So we have our grid of squares, right? So initially everything is complete. We have all the vertices, we have all the squares. Then next we're going to pick a peak. Let's say some k here as a peak of some squares. So it could be peak of this square and maybe this square. So if it's peak of these squares and they still remain in our collection, then we are going to assign these two as one collection, and then we are going to remove them from the grid. Okay, so because they are assigned already, we cannot use them anymore. We can't use the same k, we can't use all these t's, so we're going to remove them from the grid. Whatever is left, we repeat the same process. We now look at if there's any more peak that is left, then we look at all the squares that it is peak of. Once this condition is satisfied, we repeat the same process. We remove them as one collection and we move on like that. So keep repeating this, because each time we pick a k, it means that we can at least have one of these squares, right? So that means that once we can have one of these, we could always reduce the number of squares by one. So keep doing this until we cannot do it anymore. So our claim is that okay, so let's call this a lemma rather. Okay, so because this is a major result. Okay, so the lemma here is that once we stop, we can assign all elements of S to some partition. Okay, so why do we want to do this? So why we want to do this? The reason is simple. The idea here is that for each k that where sk is not empty. So if sk is not empty, it means that we have that sk is some t1 up to tm, where the accumulation at k is at least m. So this means now that if we are looking at S where sk is empty, and this is going to be the size of sk, by the way. If sk is actually empty, it's not going to be of interest, because that inequality will be satisfied automatically. So if this is empty, then the accumulation, we know, is always greater than or equal to 0, so definitely to be greater than the size of the set. So ultimately, the essence here is that we have this inequality, which we can now use to bound our sum. So remember, the total we're interested in is n, where n is sum of all these values for every k, and for each of these we have 1 plus the accumulation. So there's always going to be at least 1 plus the accumulation. If we add the 1 for every single vertex, we'll have n squared of them plus the sum over the accumulations. And for each of them, we know they satisfy this specific inequality. So we get this. And now, since sk is a partition, because we don't have any repeating, that is, the intersections are empty. That's, we have sk intersection sk prime. It's always empty when k is not k prime. That's because we pick them one at a time, and that process already ensures that we cannot have any repetitions, because once a square has been included in one, it cannot appear in any other squares again. Okay, so this is why it's going to be a partition, and that's if we assume this lemma is correct. It means that we've assigned every t to some set. So this will actually just simply be the total number when we add all the partitions together, and this will be a way of counting the number of parts. So now if you add this, it's a way of counting all the t's we could have, the number of squares we could have. So for that, let's observe what actually happens. So in this case, when n is 3, we see that we have 4 squares. So in fact, for n by n, we're going to end up with n minus 1 squares. So how does that work? We'll have, since it's n by n, we'll have n vertices in each row and n in each column. So those will end up creating vertices for our square. And from here we see that drawing this, we don't get any set of squares yet. From the second one, we can now have a first layer of squares. From the third, we get a second layer of squares. So if we do that up to the nth one, we get n minus 1 layers. And we do that for the columns as well. So we get n minus 1 by n minus 1. Okay, so altogether we have n minus 1 squared squares, unit squares. Okay, so this would be a rough estimate, and this is the value we want to show can be achieved. Okay, so to prove this inequality, it's now essential that this is actually, sk is actually a partition, meaning that even though they are disjoint, need every square to be associated with some set sk. Okay, so to prove this, I'm going to use some claims. So claim, let's see, we had claim 2, okay, claim 3. All right, so claim 3. Suppose there exists a square not yet assigned to a partition. Okay, then we must have that all peaks of t must have a peak. It could have 1, it could have 2, that all peaks of t are also not assigned. So that means we don't have such an sk for those peaks. Okay, so how do we prove this? Okay, so first of all, observe that based on the process of the algorithm, for every peak that is assigned, it means that, let's look at this algorithm again. So when we assign such a k, it means that we're going to include all the squares that are peaks of k into this, except possibly those ones that are already assigned. But that will mean that they'll be part of a previous partitioning. So definitely at this point, we'd have partitioned every single peak that is connected with every square that is having k as a peak, right? So this means that if we take it backwards, that if they were a square that's not yet assigned, that all the peaks of T are not assigned, because suppose not, then there's this K that's a peak of T, and then K is assigned, and what I just said will follow. Since K is assigned, it means that either we'd already, while we're forming K, SK, either T was already assigned, but it's not the case, in which case would have appeared among the sets T1 up to Tm, whatever M was. Okay, so this would be a contradiction. So T will be here. That'll be a contradiction. All right, so moving on to the next claim. So it's related to this one. So now suppose we have, if K is a peak not yet assigned. Okay. So what do we hope to get this time around? Then we must have that, first of all, the accumulation at K has to be exactly 3. K is a center. I'll explain what that means. And all squares that contains K are not assigned. So before we prove this, let's see what some of these things actually mean. So K being a center means that in terms of the grid, we have 3 possible arrangements if we ignore rotation and reflections. So we could have a K sitting somewhere within the grid of our squares, or we could have it somewhere at the edge. So we call this one edge. This would be a center K. This would be edge, and then we have possibly one at the corner. So these are the 3 different positionings we could have for each K. So we're saying that if we have any K that satisfies that's not yet assigned after we exhausted the algorithm, then it means that it has to be a center, and that means that it will contain 4, 2, 3, 4. So there'll be 4 squares that are attached to it, and then this part says that all of them are also not going to be assigned. Okay, so let's prove this quickly. Okay, so first of all, we have that since it's a peak from claim 2. Yeah, so from claim 2, we must have that the accumulation is at least 1. Okay, and also we must have that the accumulation is going to be less than M, where M is the number of where T1 up to Tm are not assigned, and these are the squares that have K as a peak. Okay, so we must have this inequality. Otherwise, if we have reverse, then we could continue the algorithm at this particular K and move on. And certainly we have at least one of these, right? Because we said K is a peak, all right? So from this, it means that, first of all, the most we could have about this M, the highest value you could get is when K is a center, that is 4. So this means this at least is at most 4. So this means that K, the accumulation at K will have to be between 1 and 3. Okay, so let's see what happens at each case. So if this were 1, it means that M will be greater than 1. So that means there was this T1 and T2, where K is peak of T1 and T2. So we have two possibilities. We could have them being adjacent, or we could have them meeting as at their corners. Now, what does it mean for K? So K will be somewhere here. In this case, K will be here. What does it mean for K to be a peak of both T1 and T2? It means that there will have to be a clash. If we look at just within T1 and within T2 also, there will have to be a clash. The same will apply this way. So ultimately, we see that we have a clash of the second degree here, meaning that the accumulation at K here will have to be at least 2. In the second case, it's even worse. We would have to have the accumulation being at least 3, and that will contradict the value we are actually dealing with here. So next, we'll look at, suppose it were 2, then this time the number m will have to also move up a bit. So we now have m is greater than or equal to 2. So it's greater than 2, so there will be at least 3 of them. So we could have some 3, it could be more. So at least there are 3 of them. There's only one way to arrange this in general. Just it has to be certainly it has to be a center. K will have to be a center, and only one of these might be missing. So we'll have these 3, and as peaks of each of those squares, we must have these clashes, which once again is similar to the second stuff we did here. So this will be at least 3. Accumulation at K will be at least 3. Once again, contradiction. So we are left with K equal to 3. Okay, so I want to show that this is also going to be what we need. So first of all, this aligns with what we are trying to show in this claim. So we already got the first part. So now what does this mean? We use the same argument to see what this could give. So this means that now m is greater than 3. So m has to be exactly 4. And it means that we have T1, T2, T3, T4, where K is peak of all of them. So we must have a diagram like this. So first of all, K has to be a center, and all these we are not yet assigned, which is what we wanted to show, and we're done. Okay. All right, so one more claim before. Okay, one more claim before we could prove our lemma. So claim 5 now. All right, so if we have for K as in claim 4, then we must have first of all that, so I'm just going to quickly write what this would be, not in terms of sentence, just to describe it so that we are clear about what we're talking about. Okay, so we know that K is going to have this structure where we have this going on, but each of these are squares, so they have other parts that were not included. So what we have is that we must have the accumulations here to be 0, so we must have the accumulations at this other adjacent cells to be 0. So that's the first part of this claim 5. Must have this to be 0. Otherwise, if we don't have, then the sum of the accumulations will already be at least 1, plus the number we get from the clashes, which will be 3, right? So if we add this to 3, we'll see that the total accumulation at K will now have to be at least 4, and that is wrong because this accumulation has to be exactly 3. So that means there's no carried over accumulations. This has to be 0, and not just this, but also that if if K prime is at boundary of T1, T2, T3, T4, that's this bigger square, the 2 by 2 square. So if you have a K prime at the boundary such that the accumulation at K prime is bigger than 0, then you must have that K prime is a peak of one of these squares. Okay, so we'll quickly show that. So suppose we have such a K prime. Certainly it cannot be adjacent to K, so it has to be at a a corner of this bigger 2 by 2 square. So we have accumulation 0 here, 0. We have this arrow, so it could be somewhere, let's say here, k prime k. Okay, so this value accumulation here is bigger than 0. The accumulation here is bigger than 0. So what that means is that, excuse me. Okay, so when the accumulation here is bigger than 0, it means that we cannot have the arrow here going downwards, because that accumulation will carry over to this adjacent portion, which will have to now also be greater than 0. So that is not possible. This means this arrow have to go upwards, and the same applies here. This must go upwards, and that will become a clash in that particular square, whatever it is. So let's say T1. So this will be a clash in T1, and not just that, it has to be that T1 has 2 peaks. So that must be another peak of T1. So it's going to be another peak of at least one of this, and that brings us to the end of that part. So with this, we have the right ingredients to prove our lemma that everything is actually going to be assigned at the end of the day. So we're going to suppose not. So return back to the proof of lemma. Okay, so suppose not. So what does this mean? It means that there exists at least one t not assigned. Okay. So what we're going to do is we are going to pick the a component of squares that are connected yet not assigned. So let S prime be a connected component. So I'm going to explain what this means. Component of all remaining or unassigned squares, unit squares. Okay, so that's because since we have one square, we could have some other neighbors that are not assigned. We include that, so we can keep adding, let's say, neighbors. So they have to share a side, right? So we keep adding them. So long as they share a side, and they are not assigned, we add that to our collection. So we can keep doing this, but not forever, because we only have a finite number of these squares. Eventually, we would have finished adding everything we could add. So once whatever we have left, that would be so you could go like this. Yeah, so that would be the, just increase this more to demonstrate some. Okay, so we got something like this. So this is going to be S prime, where we cannot increase it any further. So it means that every square here, all this, they are unassigned, and everything beyond that that might have been there before already assigned to something. Of course, we could have some other components that are not assigned that touches it. So long as they don't share a side, we're not going to include that in our S prime. So every element in S prime must have a neighbor that is side by side, except it's isolated. Okay, so this will be our S prime. So this S prime only exists if we are assuming there's at least one t to start with, right? So we hope to get a contradiction that such an S prime should not exist. Okay, so how do we go about this? So first of all, we have that we look at the boundary. So look at the boundary of S prime. Let me indicate a boundary here. So in this case, this would be the boundary. So this is the boundary. Okay, so once we've identified the boundary, then we see that if you look at the arrows, because some of these will have some arrows, right? All of these are uphill paths or part of uphill paths. So there are some arrows. If you look at it, all the arrows cannot face the same direction. because if they face the same direction, then we're going to get a circle. Let's say they all face clockwise direction. Then we're going to get a clockwise circle, and that's going to contradict our first lemma that we don't have any circles. So definitely we cannot have everything going one direction. So they have to be two directions that are going to clash at some point. So going one direction, we are going to have to meet another direction coming to clash with it. Otherwise, we'll just get a circle. So we must have a clash somewhere. So there's going to be a clash at somewhere in the boundary. So there exists K at the boundary where there's a clash at K. Okay, so we could have a K, let's say somewhere here, where there's a clash, meaning that one arrow is going one way along the boundary, while another is going another way. Okay, so once we have a clash, we have two things to look at. So first of all, since it's in the boundary, it means that it's going to be a vertex of some square, at least one square that's in S prime. So so that means K is vertex of some T1 that's in S prime. Okay, and also since we have a clash at K from our lemma 2, we have that the accumulation at K has to be at least 1. So with these two ingredients, we see that we can make use of claim 5. Okay, so claim 5. Why can we use claim 5? So we have a vertex of T1, right? We have a vertex of T1, and T1 is in S prime, meaning that it's not yet assigned. We have that T1 is S1, so it's not yet assigned, and we have this is greater or equal to 1. So let's see. So we have something that is not yet assigned. It's going to be part of the boundary, because for T1 itself is going to have there's this K peak of T1. So since it's not assigned, that peak implies that peak is not assigned. Okay, so peak is not assigned. Then we can use this claim 5. We're going to have this structure. That means K prime is going to end up being the boundary of some figure like this. And for such a K prime, for it to have accumulation bigger than 0, it has to be a peak of the square that actually touches it. So this means that T1 has a K as peak. Okay, let's call this K1 to avoid confusion. So T1 has K as a peak. So we must have something like this, T1 K. All right, now if you go to claim 3, you see that because K1 is now a peak of T1, because K is now a peak of T1, from claim 3, it means that and T1 is not assigned, it means that K is also not assigned, right, since it's a peak. So we have that K is not assigned. That's because T1 itself is not assigned. Okay, so since K is not assigned, now we can go ahead to use claim 4. Okay, so claim 4 once again we mean that K itself will have to be center. And not just that, and we must have this structure where T1 is just a part of it. We have other unassigned ones. So K will be at the center, and all 4 squares touching it will also not be assigned. So what does this mean? It means that K cannot be at the boundary. So this means K not at boundary of S prime, because this means we can now extend our S prime through beyond this. right? So k itself cannot be at the boundary, and that will be a contradiction of the assumption of where we started from. So k was an element on the boundary. So this becomes a contradiction, which means that ultimately what we assumed here is wrong. So this concludes the proof of the claim of the lemma. Okay, so what we just done now is we've shown what we needed, and we already have the inequality. So we've actually made use of the lemma to get this inequality. So now we want to show that this smallest possible value we've written here can actually be achieved. Okay, so we just need to show an example where that has this value. And once again, at equality, we have to understand that the only part where we use inequality in this entire inequality is just here, which came from here. So if we can make sure that we have equality here all the time, then we are done. So our goal is to show that we have, so want to create a Nordic n by n square, whereby the accumulations at each k will be precisely these values. Okay, so first of all, if we have if k is at a corner, if k is at a corner and k is equal to, so if k is at the corner and k is a peak, right? So if you have a peak at the corner, that means that this is greater than or equal to 1, but we can only have one square associated with k. So that means that sk will have to be 1. We need the clash here to be a simple clash, where this is like 0 accumulation, and then we get 1. So if we have a corner, we need this structure, and if we have an edge, and in this way we say that this particular corner square we've associated with this particular peak. Okay, then if we have another structure at k at an edge, okay, then we have this value k is greater than or equal to 2. If we have k is greater than or equal to 2, it means that both of these squares will have to be having k as peak. So we must have this to still be simple. So we must have 0, 0, 0, and we'll associate these squares, both of them, to this peak. So something like that. And then for when we are dealing with a center piece, and this is from 3 and beyond, then it means that we have a k at the center, we have these 3 coming in, these 4 coming in, and now we can associate at most 3 of them to this. So let's say we associate 1, 2, 3. It means that we cannot, because we need to have this equality, then we cannot associate this. We must have something like this associating with something else, which will have to be a twin, another peak of that particular square. So this is like just a rough idea of how we're going to construct our example. So these are the 3 major figures we have, whereby we can now associate with every peak or every accumulation a particular square, so that this equality will always stay true. So encounter just these 3 sort of figures. All right. So how do you go about this? Okay. So first of all, I'm just going to draw grid. So let's say we have something like this. Could just quickly sketch. Okay, so we're going to construct this in a way that we have a valley at the beginning. Okay, and then we're going to divide this into 2 portions. So let me use a color here. So this will be this diagonal will be a major dividing line. So we'll have two different patterns on either side. So on one side, we'll have this pattern whereby we place the peaks here only within this. So they alternate between these two. Like this. Then we'll leave one row empty. And we'll do something similar again. So this is going to be the pattern for this. Leave one row, we continue it like that. Okay. So first of all, I'm going to show why this is going to work well. So we're going to create we're going to assign each of these, associate them with a value of this peak. So first of all, for this free line, we're going to create a flow to go in one direction. So what we're going to do now is we're going to try to make sure that while creating this, there are two things to just keep in mind. They are related. So first of all, we're going to avoid making clashes that are not going to be peaks. So if we have any clash that is not a peak, that means at some point we still go over to some other part. It's going to take over this accumulation and it's going to affect the values we've established here. So these values, our ideal values will no longer be, will no longer hold, and that will create an inequality. So meaning that once we have any two uphill parts clashing, we have to form a peak at that spot immediately. Okay, meaning every other part connected to it will have to come back to that same spot. So you have to be an absolute peak, meaning irrespective of where we are coming from, it will be a peak. Okay, so that's the first thing. And then and also if we now have, this means that if we have an arrow leading to a point that's not a peak, we will have to make sure that there are no clashes. So this means we have something like what I call a split. So we will have something like this. If it's a corner, something like this. If it's at the center, it's going to look like this. So that means it just comes in and spread outward from all of this. So this means that first of all these peaks, we need to have arrows flowing towards them. Okay, so this is non-negotiable. Okay, so we just continue that pattern like that. So now what we see is that we can create along this, we see that we can create flows here when this is free. This will create a split into two parts. So if you continue like this, you see that this pattern doesn't affect any of the ideas we've set up so far. And the same way we can come to a similar line here. And for each of these, we create splits, right? Going either way. It doesn't conflict with any of the ideas we've set up so far. So we can keep doing this for every third line like that. And then once we have that, we essentially already have all the flows except for the flows on this along these parts here, which automatically can be filled alternatively like this. So we get something like this, and then we just confirm that this actually makes sense. Okay, so we see that for every point that is not an absolute peak. So for example here we'll have a split. So we just need to check they're all similar points. So we see that the same thing is going to repeat, and obviously along this free line they are all splits, so we don't have any conflicts going on. So this means that in fact we can really associate with every square, we can associate a particular peak. Okay, so I'm going to use this color next. So here we used this. So this is going to be the pattern of our association like this. And then the same from here, we could go like this towards the peaks each time. So that's because each of these squares will have exactly one peak. So there's not really much of a choice. So where we could have conflicting values is along this row once again. But once we've started this going this way, then we're going to see that once we choose, because here we have a valley here, so we need this to be a peak here. Once we decide that this should not be a peak here, then actually, let me expand this a bit so we could make this decision. I'll explain later. All right, so once we have these arrows, it means that we already have this scenario where 3 of them already meet. So the fourth one will have to like pick a new peak. So have this. Now 3 of them met again. The next one will have to pick a new peak, like that. So we see that it gets this this zigzag kind of pattern. So it gets a zigzag kind of pattern, like that, which goes outwards. So as once we extend, we can keep extending it as such. The same is going to happen here. So just repeat that same pattern. So this is the pattern on one hand. Now let me describe the pattern on the second hand. So that is going to be, so here we're going to place the peaks. So we have some initial values. So this is going to be the pattern. So where we had 3 peaks here, we ignore this one and come here. When we don't have, just take to the next one, something like that. So this is the pattern we use. Okay, once we've done this, the rest of the peaks will be drawn like this. So they'll come down like a diagonal. So that's going to be the pattern here. So why would this also make sense? So let's first of all assign each of these. So here we already had some of these arrows. This will come here, this will come here. All right. So here we must have, we are trying to avoid creating valleys. So here we must have a split. So here there are some parts that you see that it's a natural choice because we only have one peak. So once there's only one peak, we can only make that association with that particular peak. So we see that if we look at almost all the squares, there's going to be a natural choice, except those lying on the diagonal that have 2 peaks. So any other one is going to be a natural choice. Okay. So it's going to continue like that. Any other one will have a natural choice. So what happens with the ones at the diagonal? Well, once we've filled out the first one, we see that now we have 3 leading up to this peak. So this will have to choose the next second peak of this square. And now we have 3 here again. So it keep going outward to keep picking one more. So the pattern will continue. The same is going to apply everywhere else. So we'll have this arrow and it's going to keep forcing outward like that. And with this, we are going to end up having everything filled out. So this gives us a bijection between the squares and the accumulation, because now every peak we see in the middle, we have accumulation 3 and 3 squares associated with it. Those at the edge will have accumulation 2 with 2 squares associated with it, and those at the corner, wherever they appear, will have 1. So why can we be sure of that? So the reason here is that, so first of all, we have this downward trend. Okay, so why can we be sure of this? That's because all this, both the blue and the yellow waves, they are going outward, right? So this means that if at some point, generally they will all be like having this figure, but if we truncate our diagram at some point, then it's either going to make this become an edge, in which case the one among these 4 arrows that is going out would be left outward because this goes outwards. So the other 2 must remain, and then we'll have this figure. And then if we want it to be at a corner, it means we have to cut this one once more, which will just naturally give 1 corner for 1 square. Okay. The same applies here because we're going outwards once again. So if we truncate it, let's say here, cut the map here, then it's going to create the corner. If we truncate it maybe somewhere here, we see that this it's already an edge and so on like that. Okay, so what we just need now is to complete the flow on this other side. So this also will have a pattern, a simple pattern. So we're going to have, let's say we use this. Okay, so first of all, for all the peaks, we know that the arrows must all go uphill. So they are absolute peaks. So once they clash, all of them must clash at that point. So from that, we see that those squares are along the yellow axis, they will all have their arrows completed. So what will be left with will be this part here. So we'll now have something like this left. It's kind of zigzag pattern. The same applies here. So what we're going to do is we will just create our splits through that pattern to finalize it. So here we already have this going this way, this going up, and this comes this way. So we have a split. This will come down, right? And this comes this way. This will come down. So after this, once we get to this purple line, we'll just follow like this. I will see that each of these will be split. Once they come closer to any yellow square, it's going to split that way and then reflect down, split into two, and reflect like that. So this will continue this way. So we just need to make sure that this central part can be properly filled. So just do that for this portion. So this goes like this. This goes like this. This goes like this, like this, like this, and this goes like this. So must have a split here. This have to come here. Must have a split here. This comes down, and we get another zigzag pattern like that. Okay, so either way, at some point we'll be able to start our zigzag pattern and it will continue like that. So this will just keep repeating themselves and we'll have our full pattern. So this means that anywhere we truncate this diagram, would have a flow that satisfies this property. Okay, and it has only one valley, which is at the beginning. So why is this relevant, or how do we use this to? Because this doesn't really give us the example we need. The example we need to show that it's actually a possible minimum. For it to be a possible minimum, we need a Nordic square we can associate with this. So we'll have to make sure that once we have this figure, we can actually associate a Nordic square to it. So we're going to use an algorithm to actually do that. We can always do that given any flow. So how do we do it? So to assign numbers, okay, so I want to assign numbers. So let's say we truncated this at some square at the right size for our n. So that means they are now n minus 1 by n minus 1 squares here. So we now have n by n vertices. Okay, so I want to assign numbers 1 up to n squared. So we're going to just do this. First of all, 1 will be the valley. There's only one valley. We just pick the smallest number to be that valley. 1 is perfect for that. So next, this is the algorithm. So just repeat this each time. So we're going to take a look at the vertices. So if a vertex is free, that is, we've not assigned any number to it, and all the vertices that lead up to it are also free. Are not free. Then we place the next number there. Okay, so this means that we'll start with our flow, place 1 at the vertex, we pick the next number 2, we'll check if there's any vertex that is free. If it's free, we'll look at all the vertex leading up to it, because we already have all these arrows we drew. So once we see that we filled, if we find any vertex that we've not placed any number on it yet, and all the arrows leading to it, we trace them back, we see that we've already placed numbers there, then we're going to place the next number at that point. So we claim that this is going to solve the problem. Okay, so suppose it doesn't solve the problem. What does that mean? So suppose not. So that means that it's going to be a number k not yet assigned. And since this number k not yet assigned, it means there's going to be a vertex not yet assigned. That's a vertex not yet assigned. So it's going to be free. Okay, and now once we have a free vertex, clearly it's not a value. We already filled the value. So it means that we couldn't perform this algorithm anymore. It will mean that there's going to be an arrow leading up to P. So let's say this is P1. There's going to be an arrow leading up to P1 from an adjacent one, P2, whereby P2 is actually free, because suppose they are not all free, then we'll do this. So that means P2 will be free, and that means we can just repeat the same process. So P2 is free, and we cannot perform the algorithm anymore. It's not a value. So there have to be one more arrow leading up to it from some P3, where P3 is also not free. Just continue the same process. And remember, we can keep doing this, but we cannot do this indefinitely, because we have just a finite number of vertices in our flow. Okay, so at some point we have to repeat some number, and if we repeat that number, we're going to end up getting a circle, which clearly is not possible from our figure. Okay, so this means that this is not possible. So at some point we have to get to where there have to be a point where we cannot go down any further, which will have to be a value, and that will be a contradiction. Okay, so that's that for this. So I've just used one more, just finally one more just final example to see how this actually works in practice. So if you want, you can stick around. So this is just another picture of what I just drew, a much clearer picture. Okay, so let me use this. So now we're going to assign numbers. So let's say we have n equal to nothing too big. Let's n equal to 5. So that means we have 5 by 5 vertices, and the number of squares will be 4 by 4. So we have to truncate it, cut it here. So you're only interested in all this this figure. All right, so once we do this, we see that 1 will be placed here. Okay, and then we can place 2 here, because the only arrow leading up to 2 comes from 1. So because we are dealing with splits, it means that once any part is not an absolute peak, it only have one arrow leading up to it, because once we have multiple, that will have to be a peak, right? So once we have something that is not a peak, it becomes easy to fill. So we can just quickly fill this as 2, 3, 4, 5, 6. Okay, so now we've met all these obstacles. We could continue here, 7, 8, met obstacle, 9, 10, 11, could go in any direction, 12, 13, we meet obstacle, 14, 15. So we already have all this fixed, and this is perfect, because if we started with these numbers, those arrows will be exactly the same arrows that will come out, just the inequality. Okay, so now once we've done this, we see that there are still some that may be left. Okay, so we have here can move to this will be 16. So it doesn't really matter the order we do this, we just do it as much as possible. So once we've done this, we'll see that at each point, once we want to continue, we'll have to have met an absolute peak. That's these green spots. So once we've done this, for the green spots, they don't have any connection with themselves, so you can just place any of the remaining numbers anywhere among those. So you could start 19 here, 20, 21, 22, 23, 24, 25. So this, for example, will just be one example. It doesn't really matter which points you pick first, but as long as you stick to these rules, then definitely you get an example that gives exactly the same maps with these same arrows. Okay, so let's stop here for now. So this was actually longer than I expected, but Yeah, so thanks for being part of this video. I'll see you sometime later. Bye.